Tonight, we're going to talk about the deliberate death of something beautiful. On the morning of September 15th, 2017, at precisely 6:31 in the morning California time, a spacecraft that had been travelling through the darkness of the outer solar system for nearly 20 years began its final descent. It was falling into Saturn, and the people who had built it, who had guided it across billions of miles, who had loved it in the way that people come to love something they have tended for a very long time, those people had chosen for this to happen. They had chosen to destroy it. The spacecraft was called Cassini, and it had been one of the most successful machines humanity had ever sent into the void. For 13 years it had orbited the ringed giant, sending back images of such staggering beauty that they changed the way we understood our own solar system. It had discovered oceans beneath frozen moons. It had flown through geysers of ice erupting into space. It had revealed storms larger than Earth churning in Saturn's atmosphere, and it had given us more than 400,000 photographs, 400,000 windows into a world so far away that the light from our sun, travelling at 186,000 miles per second, takes more than an hour to reach it. And then, on that September morning, a small group of scientists gathered in a control room at the Jet Propulsion Laboratory in Pasadena, California, and they watched it die. What happened in those final hours surprised them. What Cassini discovered as it fell through Saturn's atmosphere, things no spacecraft had ever measured, secrets the planet had kept for 4.5 billion years, gave them one last gift. But the gift came wrapped in something that felt very much like grief, because the people in that room had done something that no mission team had done quite this way before. They had not lost their spacecraft to malfunction or miscalculation. They had not watched it drift into silence through no fault of their own. They had made a choice. They had decided, after years of discussion and debate, that Cassini would have to end this way, and they had aimed it directly into oblivion. Why would anyone do such a thing? Why would the scientists who had devoted their careers to keeping this machine alive choose to destroy it? And what did Cassini find in those last moments of its existence that made its death feel like something more than an ending? By the end of tonight, you're going to understand exactly what led to that choice. A choice that was ultimately an act of protection, even of love. You're going to understand what Cassini discovered beneath Saturn's clouds as it fell, why those discoveries caught the mission team off guard, and why the truth about its final hours is far more tender than you might expect. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why Cassini's ending matters, we have to go back to a different time. A time when the spacecraft did not yet exist, when Saturn was still a distant mystery, and when the people who would one day build this remarkable machine were just beginning to dream of what might be possible. The year was 1982, and the Voyager spacecraft had recently passed through the Saturn system, sending back the first close-up images humanity had ever seen of the ringed planet and its moons. Those images were revelatory. They showed a world of breathtaking complexity. Rings that turned out to be made of billions of individual particles, some as small as grains of sand and others as large as houses, all orbiting Saturn in an intricate cosmic ballet. They showed moons with surfaces unlike anything in the inner solar system, including one moon in particular that captured the imagination of scientists around the world. That moon was called Titan, and it was wrapped in a thick orange haze that the Voyager cameras could not penetrate. Titan was the only moon in our solar system with a dense atmosphere, a blanket of nitrogen and methane that made its surface completely invisible. The Voyager scientists stared at their photographs of this strange world, this moon larger than the planet Mercury, and they could not see through the fog. They did not know what lay beneath, and that not knowing, that tantalizing mystery replanted a seed. What if we could go back? What if we could send a spacecraft that could stay, that could orbit Saturn for years instead of flying past in a matter of days? What if we could find a way to see through Titan's haze and discover what secrets it was hiding? The seed took root slowly. These things always do. Space missions are not born quickly. They're grown over decades, through countless meetings and proposals and budget negotiations and technical challenges that would defeat anyone who was not truly devoted to the vision. But a small community of planetary scientists began to push for a return to Saturn, and at the centre of their ambition was a simple, powerful idea. They would build an orbiter and a probe. The orbiter would circle Saturn for years, studying the planet and its rings and its many moons. And the probe would do something no spacecraft had ever done. It would descend through Titan's atmosphere and land on its surface, sending back data from beneath those opaque clouds. The mission would be called Cassini-Huygens, named for two astronomers who had shaped our understanding of Saturn centuries before. Giovanni Cassini, an Italian-French astronomer working in the 17th century, had discovered the gap in Saturn's rings that still bears his name, along with 4 of the planet's moons. Christian Huygens, a Dutch mathematician and astronomer, had discovered Titan itself in 1655 and had been the first to correctly identify Saturn's rings as a flat disk surrounding the planet. Together, their names would be carried across the solar system on a machine that would reveal more about Saturn than either of them could have imagined. But building that machine would take time. It would take money. It would take the cooperation of space agencies on 2 continents, because NASA, the American Space Agency, would build the Cassini orbiter, while the European Space Agency would build the Huygens probe that would descend to Titan's surface. And it would take a particular kind of faith. Faith that the mission would survive the long years of development, faith that the spacecraft would survive the long journey to Saturn, and faith that what they found there would be worth the wait. The formal approval came in 1989. The spacecraft began to take shape in clean rooms in California and in Europe, where engineers wearing protective suits worked with tools that looked almost surgical, assembling an object that would have to survive conditions no human being would ever experience directly. Cassini grew into something remarkable, a spacecraft about the size of a small school bus, bristling with instruments and antennas and cameras, carrying the Huygens probe attached to its side like a small companion waiting for its moment. By the time it was finished, Cassini weighed more than 12,000 pounds, nearly 6 tons of metal and circuitry and ambition. It carried 12 scientific instruments, including cameras that could capture images in visible light and infrared, spectrometers that could analyse the chemical composition of atmospheres and surfaces, magnetometers that could measure the invisible field surrounding Saturn and its moons, and a radar system that could pierce through Titan's haze and map the terrain beneath. The Huygens probe carried 6 instruments of its own, designed to study Titan's atmosphere during descent and, if all went well, to continue gathering data from the surface. The launch came on October 15, 1997, from Cape Canaveral in Florida. Cassini rose into the pre-dawn darkness on a column of fire carried by a Titan IV rocket, the most powerful expendable rocket in the American fleet. Within an hour, the rocket had done its work and Cassini was falling toward the sun, beginning a journey that would take nearly 7 years. 7 years. It is worth pausing on that number. 7 years to cross the gulf between Earth and Saturn, travelling not in a straight line but in a carefully choreographed dance designed to steal energy from the planets themselves. Cassini would swing past Venus twice, picking up speed from the planet's gravity, then loop back past Earth for another gravitational boost, then fly past Jupiter for one final acceleration before arcing outward toward its destination. This technique, called gravity assist, is one of the elegant tricks that allows us to send spacecraft to the outer solar system without requiring rockets of impossible size. The planets become stepping stones, and the spacecraft becomes a stone skipping across the cosmic pond. During those 7 years, the mission team waited. They monitored Cassini's systems from their control room in Pasadena, watching for any sign of trouble, sending commands across the growing distance, and dreaming of what they would find when the spacecraft finally arrived. Some of them had been working on this mission since the early conceptual stages, when Cassini was nothing more than sketches and equations. By the time the spacecraft reached Saturn, they would have spent half their careers preparing for this moment. And then, on July 1st, 2004, Cassini arrived. The spacecraft fired its main engine for 96 minutes, slowing down just enough to be captured by Saturn's gravity. It threaded the needle between the planet's outermost rings, passing through a gap that the mission planners had studied obsessively but had never seen up close. If they had miscalculated, if the gap had been filled with particles large enough to damage the spacecraft, the mission would have ended before it truly began. But Cassini passed through unharmed, and when the engine burn was complete, it was no longer a visitor. It was a resident of the Saturn system, bound by gravity to orbit this distant world for as long as its fuel and its instruments held out. The first images came back and took the world's breath away. Saturn filled the frame, amber and gold and cream, banded with storms, encircled by rings that seemed impossibly delicate given their vast scale. The rings stretched outward from the planet like the grooves on a cosmic record, each one made of countless particles of ice and rock, some as fine as smoke and others as large as mountains. The planet itself was a giant made mostly of hydrogen and helium, with no solid surface to speak of, just an atmosphere that thickened gradually into liquid and then into something stranger still, a mantle of metallic hydrogen crushed by pressures that no laboratory on Earth can replicate. But it was the moons that would prove most surprising. Saturn has more than 80 known moons, ranging from tiny irregular rocks captured from the distant Kuiper belt to worlds large enough to be planets in their own right. Cassini would visit many of them over the coming years, but 2 moons in particular would transform our understanding of where life might exist in the universe. The first was Titan. 6 months after Cassini's arrival, on Christmas Day 2004, the Huygens probe separated from the orbiter and began its solo journey toward the orange moon. It fell for 20 days, coasting toward Titan's atmosphere, and then, on January 14, 2005, it hit the haze and began its descent. For 2 hours and 27 minutes, Huygens fell through Titan's atmosphere, its parachute slowing its descent, its instruments tasting the alien air and measuring everything they could. The probe sent data back to Cassini, which relayed it across the solar system to the waiting scientists on Earth. And what those scientists saw amazed them. Titan had rivers, Titan had lakes, Titan had coastlines and channels and drainage patterns that looked remarkably like the landscapes of Earth. But the rivers were not filled with water. They were filled with liquid methane and ethane, hydrocarbons that exist as gases on our warm planet, but flow as liquids in the frigid cold of Titan, where surface temperatures hover around minus 290 degrees Fahrenheit. It was a world with a weather cycle, just like Earth, except the rain was methane and the snow was organic compounds drifting down from the hazy sky. Huygens landed on a surface that crunched beneath its weight, like wet sand or a thin crust of ice. It continued transmitting for another 72 minutes before its batteries died, giving humanity its first, and so far, only direct glimpse of Titan's surface. The images it sent back showed a landscape of rounded pebbles, not rocks exactly, but lumps of water ice smoothed by flowing liquid, sitting in what appeared to be the bed of a dry riverbed that would occasionally flood with hydrocarbon rain. Cassini, meanwhile, continued its work from orbit, using its radar to map Titan's surface through the haze, revealing a world of hydrocarbon seas concentrated near the North Pole, some of them larger than the Great Lakes of North America. One sea, named Kraken Mare after the legendary sea monster, is larger than the Caspian Sea, the biggest enclosed body of water on Earth. Titan had an entire cycle of weather and geology that echoed our own planet's systems, and it became one of the most fascinating places in the solar system, a laboratory for understanding how chemistry might lead to biology, under conditions utterly unlike our own. But it was the second moon that would ultimately determine Cassini's fate. The moon was called Enceladus, and it was small, barely 300 miles across, small enough to fit comfortably within the borders of a medium-sized American state. Before Cassini arrived, Enceladus was considered a frozen, geologically dead world, interesting but not extraordinary. The Voyager spacecraft had seen it briefly during their flybys, noting that its surface was covered in ice and marked by relatively few impact craters, suggesting that something had resurfaced parts of the moon relatively recently in geological terms. But no one expected what Cassini would find. In 2005, during one of its first close passes by Enceladus, Cassini's magnetometer detected something strange, a disturbance in Saturn's magnetic field near the moon's south pole. The disturbance suggested that something was interacting with the magnetic field, something emerging from the moon itself. The scientists asked for a closer look, and in subsequent flybys, Cassini confirmed what seemed almost impossible. Enceladus was erupting. Massive plumes of water vapour and ice particles were blasting from the moon's south polar region, shooting up through cracks in the ice, cracks that would come to be called the tiger stripes because of their distinctive appearance, and extending hundreds of miles into space. The tiny moon, which should have been frozen solid, was venting its interior into the vacuum, and not just water. When Cassini flew through those plumes and tasted their contents, it found something remarkable. The spray contained not only water ice but also sodium salts, silica grains and organic molecules. The silica grains in particular told a story. On Earth, silica grains of that specific type form only one way, through hydrothermal activity, hot water interacting with rock at the bottom of an ocean. The grains coming from Enceladus suggested the same process was happening there, deep beneath the ice. Enceladus had an ocean, a liquid water ocean, hidden beneath its frozen crust, kept warm by tidal heating as Saturn's gravity flexed and squeezed the moon's interior. And at the bottom of that ocean, hot water was flowing through rock, creating conditions startlingly similar to the hydrothermal vents at the bottom of Earth's oceans, the very vents where many scientists believe life on our own planet may have begun. This discovery changed everything. Before Enceladus, the search for life beyond Earth focused primarily on Mars, a planet that might have had water in its distant past, and on the possibility of building telescopes powerful enough to study the atmospheres of planets around other stars. But Enceladus offered something different, a world where the ingredients for life existed right now, today, in our own solar system: water, heat, organic chemistry. And the ocean was accessible in a sense. Its contents were being sprayed directly into space, where a future spacecraft could fly through and sample them without ever having to land. The astrobiologists were ecstatic. The mission planners were stunned. And slowly, quietly, a new concern began to take shape in the minds of the people responsible for Cassini's future. The concern was contamination. Cassini had been built on Earth, assembled by human hands in facilities that, while extraordinarily clean, were not sterile. Microbes can survive in remarkable places, in the cracks of spacecraft components, in the residues of human contact, in the spaces between circuits and the joints between panels. Despite extensive efforts to minimize biological contamination, no spacecraft launched from Earth can be guaranteed to be completely free of microbial hitchhikers. Most of the time, this does not matter. Most places in the solar system are so hostile to life that any contamination would be quickly destroyed. But Enceladus was different. Enceladus had liquid water and warmth and organic chemistry. If Cassini were to crash into Enceladus, either through malfunction or misfortune, there was a small but real chance that some of those hitchhiking microbes might survive. They might find their way into the ocean beneath the ice. They might contaminate an environment that scientists desperately wanted to study in its pristine state. And in the worst case, they might make it impossible to ever know whether life detected in that ocean was native to Enceladus, or merely an invasive species from Earth. The same concern applied to Titan, with its organic chemistry and its potential for prebiotic processes. The scientists who had worked so hard to study these moons now faced an uncomfortable question. What happens when Cassini runs out of fuel? A spacecraft in orbit requires fuel to maintain that orbit, to make course corrections, and to perform the maneuvers needed to visit different moons and different regions of the Saturn system. Cassini had carried a limited supply, carefully budgeted, across what was originally planned as a 4-year primary mission. But the spacecraft had performed so well, and its discoveries had been so significant, that the mission was extended, first for 2 years, then for another 7. By 2017, Cassini had been orbiting Saturn for 13 years, and its fuel tanks were nearly empty. When the fuel ran out, Cassini would become uncontrollable. It would continue orbiting Saturn, but without the ability to make course corrections, its path would become unpredictable over time. Gravitational interactions with Saturn's moons would nudge it this way and that, and eventually, perhaps in a few years, perhaps in a few decades, it would collide with something. The scientists could not guarantee that it would not hit Enceladus. They could not guarantee that it would not hit Titan, and so they faced a choice. They could let Cassini drift, allow chance to determine where it would end up, and accept the risk that their beloved spacecraft might contaminate one of the very worlds it had helped them understand. Or they could take matters into their own hands, using the last of Cassini's fuel to send it somewhere safe, somewhere it could do no harm. The decision was not made lightly. The people who loved Cassini, who had spent decades working on the mission, who had celebrated its discoveries and nursed it through every crisis, were being asked to choose its end. Some of them struggled with the idea. It felt wrong to destroy something that was still working, still healthy, still capable of gathering data. But the arguments for protection were compelling. Enceladus might harbour life. That possibility, however remote, demanded respect. The whole point of exploring these worlds was to understand them as they truly are, not as they might become after we accidentally seeded them with our own biology. Planetary protection, the field dedicated to preventing contamination between worlds, had strict protocols for exactly this situation. A spacecraft at the end of its life, with uncertain trajectory control, in a system containing potentially habitable moons, needed to be disposed of responsibly. Saturn itself offered the perfect solution. The planet had no solid surface to contaminate. It was made of gas and liquid, with temperatures and pressures that would destroy any spacecraft almost instantly. If Cassini were sent into Saturn's atmosphere, it would be vaporized within seconds, its components scattered into the churning clouds, its potential contaminants eliminated forever. The mission team began planning what they called the grand finale. The grand finale was not simply an ending. It was designed to be a culmination, a final act of science that would make Cassini's death productive. Rather than simply diving into Saturn immediately, the spacecraft would first undertake a series of orbits unlike anything it had attempted before. It would fly closer to Saturn than any spacecraft had ever flown, threading the gap between the planet's atmosphere and the inner edge of its rings, passing through a region that remained unexplored throughout all of Cassini's previous years at Saturn. These final orbits were risky. The gap between Saturn and its rings had never been studied up close, and there was a chance that it contained debris or particles dense enough to damage or destroy the spacecraft. But the potential rewards were enormous. By flying so close to Saturn, Cassini could measure the planet's gravity field with unprecedented precision, helping scientists understand its interior structure. It could sample the tenuous material at the inner edge of the rings. It could study Saturn's magnetic field from closer than ever before. And it could take images of the planet and its rings from perspectives that no camera had ever captured. 22 times Cassini dove through that narrow gap between Saturn and its rings. 22 times it emerged safely, sending back data that the mission team had waited decades to receive. And then, on September 15th, 2017, it made its 23rd and final dive, this time aiming not for the gap but for the atmosphere itself. The scientists gathered in the control room at JPL knew that this would be the last day. They had planned for it, prepared for it, and yet as the hours passed and the final signals came in, many of them found themselves surprised by the intensity of their emotions. This was not just a machine they were saying goodbye to. It was a companion, a collaborator, a faithful presence that had been part of their lives for longer than some of them had been married, longer than their children had been alive. In the final days before the dive, Cassini turned its cameras toward Earth. The planet appeared as a tiny pale blue dot, barely visible between the ice particles of Saturn's rings, an echo of the famous pale blue dot image taken by Voyager 1 decades earlier. Everyone who had ever worked on Cassini, everyone who had ever loved someone on that distant speck was captured in that frame. The spacecraft took the picture and sent it home, a farewell and a gift, and then it turned towards Saturn and began to fall. The spacecraft fell faster and faster, pulled by the gravity of a planet with more than 90 times the mass of Earth. Its thrusters fired continuously, trying to keep its antenna pointed toward home, fighting the thickening atmosphere that pushed against its surfaces. The mission team had programmed Cassini to transmit data for as long as possible, right up until the moment when the connection was lost. They expected the spacecraft to survive for perhaps a minute or two after entering the atmosphere. They expected it to send back measurements of Saturn's upper layers, data that no spacecraft had ever gathered before, information about the composition and structure of a gas giant's atmosphere that would answer questions scientists had wondered about for generations. What they did not expect was just how strange that atmosphere would turn out to be. As Cassini fell, its instruments began detecting something puzzling. The gap between Saturn and its innermost ring was surprisingly empty, far less dusty than models had predicted. The material falling from the rings into the planet was not behaving the way scientists thought it would. And the composition of Saturn's upper atmosphere contained surprises that challenged existing theories about how the planet had formed and evolved. The data came in bursts, each packet travelling across nearly 1 billion miles of space, taking 83 minutes to reach the receivers on Earth. By the time the scientists in Pasadena saw Cassini's final measurements, the spacecraft had already been gone for more than an hour. They were watching a memory, receiving messages from something that no longer existed, and yet those messages contained revelations. Saturn's atmosphere had more complex organic molecules than expected. The magnetic field behaved strangely, suggesting that the planet's interior structure was different from what models had predicted. The spacecraft detected an unexplained influx of material from the rings, hinting at processes that scientists were only beginning to understand. And then the signal wavered, weakened, and disappeared. The mission controllers watched their screens, knowing that the antenna had finally lost its battle against Saturn's atmosphere, knowing that somewhere out there, 83 minutes in the past, Cassini had tumbled, broken apart, and burned. The spacecraft that had travelled 4.9 billion miles, that had made 294 orbits of Saturn, that had discovered oceans and geysers and rings of impossible delicacy, was now nothing more than atoms scattered through an alien sky. Someone in the control room began to cry. Others embraced. The project manager, Earl Mays, announced the loss of signal with a voice that trembled slightly, saying words that the team had rehearsed but that still carried the weight of genuine grief. The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft. I hope you are all as deeply proud of this amazing accomplishment. Congratulations to you all. This has been an incredible mission, an incredible spacecraft, and you are all an incredible team. In the silence that followed, the scientists began the long work of understanding what Cassini had found in its final moments. The last gift from a machine that had given them so much, the parting words of a faithful companion that had been sent to die so that the worlds it loved might remain unspoiled. And perhaps the strangest thing of all was this. The death they had planned, the ending they had chosen, had become something unexpectedly beautiful. Cassini did not simply vanish. It became part of Saturn, its atoms mingling with the atmosphere of the planet it had studied for 13 years. In a sense, it had gone home. Not to Earth, but to the world that had become its true residence. The world it had come to know more intimately than any spacecraft had ever known any planet. There is something in that image, a machine dissolving into the clouds of a distant giant, that feels less like an ending and more like a transformation. The scientists chose to destroy Cassini, yes, but they also chose to give it back to the universe, to let it become part of the very thing it had spent its life exploring. The question now is why this matters, why the choice to end Cassini this way reveals something deeper about who we are and what we value, and why the data it gathered in those final hours continues to surprise the scientists who thought they knew what to expect. To understand that, we need to look more closely at what Cassini actually found, not just in its last moments but throughout its long and extraordinary life, and at the people who made it possible. The story of Cassini begins not at Saturn, but in a room full of dreamers, decades before the spacecraft ever existed, when the idea of sending something to the ringed planet was still considered by many to be an act of beautiful foolishness. In the early 1980s, scientists at the Jet Propulsion Laboratory and their European counterparts began sketching out what they called a grand tour of the outer solar system, a mission that would visit not just one world but many, that would study not just a planet but an entire system of moons and rings and mysteries. They called it Cassini-Huygens, naming the orbiter after the Italian astronomer Giovanni Cassini, who had discovered several of Saturn's moons and the largest gap in its rings in the 17th century, and the probe after Christian Huygens, the Dutch scientist who had first identified Titan as a moon, and had spent his life wondering what secrets that strange haze-shrouded world might hold. The mission they envisioned was ambitious beyond anything that had been attempted before. Previous spacecraft had visited Saturn only briefly, Pioneer 11 in 1979, then Voyager 1 and Voyager 2 in 1980 and 1981, passing through the system in a matter of days, snapping photographs and taking measurements before continuing their journeys into the outer darkness. Those flybys had revealed tantalizing glimpses of a world far more complex than anyone had imagined. Rings that were not solid but composed of countless individual particles, moons that ranged from tiny irregular fragments to worlds larger than Mercury, and an atmosphere banded with storms that had been raging for centuries. But the Voyager spacecraft, for all their brilliance, could only offer a taste. They were travellers passing through, not residents. What the scientists wanted was something that would stay. The Cassini mission was designed to orbit Saturn for 4 years, a duration that seemed almost indulgent at the time, when most planetary missions measured their encounters in hours or days. 4 years of continuous observation. 4 years to watch the seasons change on a world where a single year lasted nearly 3 decades. 4 years to study the rings from every angle, to map the surfaces of dozens of moons, to peer beneath Titan's opaque atmosphere and discover what lay hidden there. It was a vision of such scope that many doubted it could ever be realized. The spacecraft would need to be larger and more capable than anything previously sent to the outer solar system. It would need to carry instruments from multiple countries, coordinating the efforts of scientists who spoke different languages and operated under different institutional pressures. It would need to survive for years in the harsh environment around Saturn, where temperatures plunged to nearly 200 degrees below 0 Celsius, and radiation from the planet's magnetic field could fry unshielded electronics. And it would need funding, vast amounts of funding, sustained over decades through changes of government and shifts in scientific priorities and economic recessions that would strain every budget. The total cost of the Cassini-Huygens mission, from its earliest planning stages to the moment the spacecraft burned up in Saturn's atmosphere, would exceed $3 billion. Some questioned whether any single mission could justify such an expense. Others argued that the questions Cassini might answer, questions about the formation of planets, the conditions for life, the nature of the solar system we call home, were worth almost any price. The spacecraft that eventually emerged from this long process of dreaming and planning and negotiation was a marvel of engineering. Standing more than 22 feet tall and weighing nearly 6 tons fully fueled, Cassini was the largest and most complex interplanetary spacecraft ever built at the time of its launch. Its body was dominated by a high-gain antenna nearly 4 meters across, a dish that would beam data back to Earth across the vast distances of the outer solar system. Mounted around its frame were 12 scientific instruments, each designed to probe a different aspect of Saturn's realm. Cameras that could capture images of extraordinary detail, spectrometers that could analyze the composition of atmospheres and surfaces, magnetometers that could measure the subtle fluctuations of magnetic fields, radar that could pierce the clouds of Titan and reveal the landscape beneath. Tucked against Cassini's side was Huygens, the European-built probe that would separate from the orbiter and descend through Titan's atmosphere. The only moon in the solar system with a substantial atmosphere, a world wrapped in haze so thick that no telescope on Earth had ever glimpsed its surface. Huygens was designed to survive that descent, transmitting data back to Cassini as it fell, and perhaps even continuing to broadcast for a few minutes after landing on whatever surface it might find. It was, in a sense, 2 missions in one. Cassini the observer, circling and watching and measuring for years, and Huygens the explorer, making a single dramatic plunge into the unknown. The spacecraft launched on October 15th, 1997, rising from Cape Canaveral on a pillar of fire, beginning a journey that would take nearly 7 years before it ever reached its destination. 7 years of coasting through the inner solar system, looping past Venus twice, and Earth once to gather the gravitational momentum it needed to reach Saturn's distant orbit. 7 years in which the scientists who had designed its instruments grew older, in which graduate students became professors and engineers retired, and children were born who would themselves grow up to analyze Cassini's data. The journey was so long that some of the people who had first imagined the mission did not live to see it arrive. On July 1st, 2004, after travelling 2.2 billion miles, Cassini fired its main engine for 96 minutes, slowing itself just enough to be captured by Saturn's gravity. The spacecraft had arrived, and what it found in the months and years that followed would transform our understanding of the outer solar system in ways that the mission's planners had never anticipated. The rings were the first revelation. From Earth, even through the most powerful telescopes, Saturn's rings appear as smooth, elegant structures, solid bands of matter encircling the planet like the brim of a cosmic hat. But Cassini's cameras revealed them to be something far more complex and dynamic. The rings were not solid, but composed of countless individual particles, ranging in size from grains of sand to chunks as large as houses, all orbiting Saturn in a vast flattened disk. And they were not static, but constantly churning, shaped by gravitational forces that created waves and ripples and structures of astonishing intricacy. The spacecraft photographed features that had never been seen before. propeller-shaped disturbances caused by small moonlets embedded within the rings, vertical structures that rose above the ring plane like jagged peaks, spokes of dark material that rotated across the rings and then faded away. It watched as tiny shepherd moons herded particles into narrow ringlets, their gravitational influence sculpting boundaries as sharp as knife edges. It measured the composition of the ring material and discovered that it was almost pure water ice, dazzlingly bright and surprisingly young, perhaps only 100 million years old, a fraction of the age of the solar system itself. This was a mystery that Cassini could identify but not fully solve. Where had the rings come from, and why did they seem to be a relatively recent addition to Saturn's adornment? But the rings, for all their beauty, were only part of the story. Saturn possesses more than 80 known moons, and Cassini would eventually study dozens of them, revealing each to be a world unto itself. There was Mimas, small and icy, bearing a crater so large that it gave the moon an uncanny resemblance to the Death Star from science fiction films. There was Iapetus, half bright and half dark, as if someone had dipped one side of it in coal. There was Hyperion, tumbling chaotically through space, its surface pocked with deep craters that gave it the appearance of a giant sponge. Each moon had its own story, its own history, its own mysteries waiting to be unravelled. And then there was Enceladus. Small and seemingly unremarkable at first glance, Enceladus had been visited briefly by the Voyager spacecraft, which had noted that its surface was unusually bright and smooth in places but had moved on without lingering. Cassini would discover that this little moon, barely 300 miles across, small enough to fit comfortably within the borders of Arizona, harboured one of the most astonishing secrets in the solar system. In July 2005, Cassini flew past Enceladus at close range, its instruments trained on the moon's icy surface. What it found was almost impossible to believe. Near the moon's south pole, Cassini detected geysers, jets of water vapour and ice particles erupting from fractures in the surface, shooting hundreds of miles into space. The little moon was alive, geologically speaking, venting material from its interior in dramatic plumes that were visible in Cassini's cameras as ghostly fountains of ice crystals catching the distant light of the sun. The implications were staggering. For water to exist in liquid form beneath the surface of Enceladus, there had to be a source of heat, some internal engine warming the moon's interior despite its location in the frozen outer reaches of the solar system, nearly 1 billion miles from the sun. Scientists determined that tidal forces from Saturn and its other moons were flexing Enceladus's interior, generating friction and heat, maintaining a liquid ocean beneath miles of ice. And not just water, Cassini's instruments detected organic molecules in the plumes, complex carbon compounds of the kind that on Earth are associated with life. Here was a world that no one had expected, a moon that by all rights should have been a frozen, geologically dead ball of ice, but that instead possessed liquid water, chemical energy, and organic molecules, 3 of the key ingredients that scientists believe are necessary for life as we know it. Enceladus became one of the most tantalizing targets in the search for extraterrestrial biology, a place where life might exist today, swimming in dark oceans beneath a shell of ice, warmed by forces that had nothing to do with sunlight. And it was this discovery, more than any other, that would eventually lead to Cassini's chosen death. Because if Enceladus might harbour life, then it must be protected. Any spacecraft that crashed onto its surface, carrying hitchhiking microbes from Earth, could contaminate that pristine environment, could confuse future searches for native organisms, could potentially introduce terrestrial biology to an alien world. The scientists who had sent Cassini to Saturn found themselves confronting an unexpected moral question. How do you explore a place that might be alive without destroying the very thing you came to find? The answer, they decided, was to make absolutely certain that Cassini could never touch Enceladus or Titan. And the only way to guarantee that, with the spacecraft running low on fuel and its systems slowly degrading, was to destroy it deliberately, to plunge it into Saturn itself, where no moon could ever be contaminated, where the spacecraft would be vaporized so completely that not a single microbe could survive. Titan too played a role in this decision. The largest of Saturn's moons, bigger than the planet Mercury, Titan had been the other great target of the Cassini-Huygens mission. And what the mission revealed about this strange world was no less astonishing than what it found at Enceladus. On January 14, 2005, the Huygens probe separated from Cassini and began its descent through Titan's thick orange atmosphere. For 2.5 hours the probe fell, its instruments sampling the air around it, its cameras capturing images of a landscape emerging from the haze. What Huygens found was a world that seemed hauntingly familiar and utterly alien at the same time. Titan's atmosphere is composed primarily of nitrogen, like Earth's, but laced with methane and other hydrocarbons that give it its distinctive orange colour. The surface pressure is about 50% higher than on Earth, the only place in the solar system besides our own planet where a human could stand in a substantial atmosphere without being crushed. But the temperature is nearly 200 degrees below 0 Celsius, so cold that water ice is as hard as rock, and methane exists not as a gas but as a liquid, filling lakes and rivers and seas. As Huygens descended, it photographed channels carved into the landscape, drainage patterns that looked remarkably like river systems on Earth, except that the liquid flowing through them was not water but liquid methane. The probe touched down on a surface that gave slightly beneath its weight, a surface strewn with rounded pebbles made of water ice, smoothed by flowing liquid in some past epoch. Huygens continued to transmit data for 72 minutes after landing, far longer than anyone had expected, before its batteries finally failed and it fell silent. Cassini, meanwhile, continued to study Titan from orbit, using its radar to peer beneath the moon's opaque atmosphere and map its surface. It discovered vast seas of liquid hydrocarbons near Titan's poles, bodies of methane and ethane larger than the Great Lakes, the only stable bodies of liquid on any surface in the solar system besides Earth. It watched weather systems form and dissipate, clouds of methane drifting across the landscape, occasional rainstorms that must have fallen as a slow, oily drizzle. It found mountains and dunes and craters, a landscape shaped by processes that were familiar in their outlines but utterly exotic in their chemistry. Titan, like Enceladus, became a world of profound interest to astrobiologists. Its complex organic chemistry, driven by the interaction of sunlight with its methane-rich atmosphere, was producing molecules that might be precursors to life, or perhaps in some utterly alien form life itself. The possibility that living organisms might exist on Titan, using liquid methane instead of liquid water, breathing hydrogen instead of oxygen, was speculative but not impossible. And if such life existed, it too must be protected from contamination. The decision to end Cassini's mission by plunging it into Saturn was made years before the final dive, built into the mission plan as fuel supplies dwindled and the spacecraft's systems began to age. The scientists called it the Grand Finale, a deliberate echo of the Grand Tour that had inspired the mission in the first place. But unlike the Grand Tour, which was about discovery, the Grand Finale was about responsibility. It was about honouring the possibility that the places Cassini had found might be more precious than the spacecraft itself. In the months before the final plunge, Cassini performed a series of 22 orbits that took it between Saturn and its innermost ring, threading a gap that no spacecraft had ever traversed. These orbits were themselves remarkable achievements, requiring precise navigation through a region where collision with even a small ring particle could have ended the mission prematurely. But Cassini survived each pass, gathering data about Saturn's gravitational field, its magnetic environment, and the mysterious rain of material falling from the rings into the planet's atmosphere. The scientists who analysed this data discovered something unexpected. Material from the rings was spiralling inward towards Saturn at a much higher rate than anyone had predicted. Ring particles, pulled downward by gravity and dragged by the planet's magnetic field, were raining into Saturn's atmosphere at a rate of thousands of pounds per second. This rain was composed not just of water ice, but of organic molecules, silicate grains, and other materials that had accumulated in the rings over millions of years. The rings, it seemed, were slowly dissolving, feeding themselves to the planet they adorned. Some calculations suggested that at this rate, Saturn's rings might disappear entirely within a few 100 million years, a long time by human standards, but a blink in the 4.5 billion year history of the solar system. This was a profound discovery, one that reshaped scientific understanding of Saturn's rings. They were not eternal features of the planet, but temporary decorations, perhaps created by the destruction of a moon or the capture of a comet relatively recently in cosmic terms. The Saturn that future generations might visit tens or hundreds of millions of years from now, might look very different from the Saturn that Cassini had spent 13 years exploring. The rings might be thinner, fainter, perhaps gone altogether. What Cassini had witnessed and recorded might be a privileged view, a snapshot of a world in a particular phase of its evolution, a phase that would not last forever. And this knowledge, too, came from Cassini's final months, from the risky orbits that threaded the gap, from the instruments that continued to function long past their design lifetimes, from the spacecraft's willingness to go where it had never been sent before. The grand finale was not just a farewell, but a final act of scientific generosity, a gift of data that would take years to fully analyse and understand. The people who had built Cassini, who had tended it for 2 decades, who had celebrated its discoveries and worried over its malfunctions, felt the approach of its end with a complicated mixture of emotions. There was pride, certainly. Pride in what the mission had accomplished, in the worlds it had revealed, in the questions it had answered and the new questions it had raised. But there was also grief, a genuine sense of loss for a machine that had become, over the years, something more than a collection of instruments and circuits. The scientists spoke of Cassini with affection, describing its personality, its quirks, its stubborn reliability. They had spent so many years watching it work, interpreting its data, worrying about its health, that they had developed a relationship with it that was not entirely rational, but was deeply felt. Earl Mays, the project manager who had announced the loss of signal on September 15th, 2017, later said that saying goodbye to Cassini was harder than he had expected. "I thought I would be okay," he said. "I'd been preparing for this for years, but when the moment came, it hit me harder than I anticipated." The night before the final plunge, the Cassini team gathered at the Jet Propulsion Laboratory for what they called the last looks, a final observation session in which they trained the spacecraft's cameras on Saturn, its rings and its moons one more time, capturing images that would be the last ever taken by this particular set of eyes. They photographed Titan, the world that Huygens had explored and that Cassini had mapped so thoroughly. They photographed Enceladus, the small moon with its hidden ocean, where perhaps something lived that had never seen starlight. They photographed the rings, those impossible structures of ice and rock, and the planet itself, vast and golden and striped with storms. Some of those images were released to the public, shared as a farewell from a spacecraft that had become, in its way, a beloved ambassador of humanity to the outer solar system. They were pictures taken by a machine that would soon cease to exist, final glimpses of a world that would continue to turn and change and endure long after the observer was gone. There was something poignant in those images, something that transcended their scientific value. They were postcards from the edge of forever, messages sent back by a traveller who knew it would not be returning. And then, in the early hours of September 15th, Cassini began its final descent. The spacecraft had been oriented so that its antenna pointed toward Earth, maintaining the radio link that would carry its last transmission across 800 million miles of empty space. Its thrusters fired periodically tiny corrections to keep that antenna aimed precisely at the blue dot, where its creators waited and listened. The atmospheric instruments were active, sampling the air of Saturn for the first time, tasting molecules that no human-made device had ever touched. The mass spectrometer detected water, ammonia, methane, and more complex organic molecules, the raw materials of a world that had been forming and reforming for billions of years. The data flowed back to Earth, each measurement a small miracle of engineering and physics, a message travelling at the speed of light across a void so vast that it took an hour and a half to arrive. And the scientists in Pasadena, watching the numbers scroll across their screens, knew that they were seeing something precious, not just data about a distant planet, but the final thoughts of a companion they would never hear from again. Saturn's atmosphere grew denser around Cassini, pushing against the spacecraft with increasing force. The engineers had calculated when the pressure would become too great, when the forces on the antenna would overcome the thruster's ability to compensate, when the spacecraft would finally tumble and lose its lock on Earth. They had estimated that this would happen about a minute into the atmospheric entry, at an altitude roughly 900 miles above Saturn's cloud tops. But these were estimates based on models, and models are never perfect. Saturn itself would have the final say. At 36 seconds past 7:47 in the morning California time, the signal from Cassini abruptly ended. The engineers watched as their screens, which had been filled with streaming telemetry, went silent. There was no static, no gradual fade, just a clean termination, as if someone had flipped a switch. And in that moment, they knew that Cassini was gone. The room fell quiet. Not the quiet of anticipation, which has energy in it, but the quiet of finality, which has only stillness. For 20 years they had listened to Cassini's voice, its telemetry, its data packets, its steady confirmation that yes, it was still there, still working, still faithfully carrying out the instructions they sent. And now that voice had stopped, and it would never resume. Some of the engineers wept. Others simply sat, staring at screens that showed nothing, struggling to comprehend that the spacecraft they had tended for so long was now dispersing into Saturn's winds, its components scattering across the atmosphere of the planet it had orbited for 13 years. The control room, usually a place of focused activity, became something closer to a memorial service, a gathering of people who had come to say goodbye to something they loved. Earl Mays, the mission's project manager, spoke to the assembled team. "The signal from the spacecraft is gone," he said, "and within the next 45 seconds so will be the spacecraft." His voice was steady, but the words carried the weight of an ending that could not be undone. "I hope you're all as deeply proud of this amazing accomplishment. Congratulations to you all. This has been an incredible mission, an incredible spacecraft, and you're all an incredible team." And then, because grief and celebration are sometimes the same thing, the room broke into applause. They applauded Cassini, and they applauded each other, and they applauded the strange, beautiful privilege of having sent a piece of themselves to Saturn and watched it work perfectly for 2 decades. It was not a triumphant applause, not the kind you hear when something succeeds. It was something softer, acknowledgement, perhaps, or gratitude. A way of saying that this had mattered, that the work had been worth doing, that the loss was real precisely because the mission had been so good. In the hours and days that followed, the data from Cassini's final plunge began to reveal its secrets, and those secrets were, as the mission scientist would later say, full of surprises. Picture, if you can, what Cassini encountered in those last 93 seconds of its existence. It had been falling towards Saturn at over 75,000 miles per hour, a speed so great that the atmosphere it was entering felt less like air and more like a wall. But Cassini was built to withstand a great deal, and its instruments remained active and transmitting until the very end, gathering information about a region of Saturn that no spacecraft had ever touched. The ion and neutral mass spectrometer, the instrument that could taste the chemical composition of whatever surrounded the spacecraft, was working beautifully. It had been designed decades earlier, built by scientists and engineers who could only imagine what it might one day sample. And now, in the final minute of Cassini's life, it was sampling Saturn itself, breathing in the atmosphere of the solar system's great ring-bearer. What it found surprised everyone. The scientist had expected Saturn's upper atmosphere to be relatively simple, mostly hydrogen, the lightest and most abundant element in the universe, mixed with helium, the second lightest. This was, after all, what decades of observations had suggested. Saturn is classified as a gas giant, a world made almost entirely of these 2 elements, compressed into a sphere so vast that more than 700 Earths could fit inside it. The atmosphere should have been predictable. It should have confirmed what the textbooks said. But Saturn, it turned out, had not read the textbooks. The mass spectrometer detected far more complex molecules than anyone had anticipated. There was methane. Yes, that was expected. But there were also heavier organic compounds, molecules containing carbon and hydrogen, in configurations that the scientists struggled to explain. Where were these molecules coming from? How were they being produced in an atmosphere that should have been dominated by simple gases? The data suggested that Saturn's upper atmosphere was far more chemically active than the models had predicted, a place where surprising reactions were occurring, where the raw materials of organic chemistry were being assembled in ways that no one had foreseen. This was, in its quiet way, a discovery that raised more questions than it answered, and that is perhaps the most honest thing science can do, not to close the book on a world, but to open new chapters that future missions will someday have to read. There was more. Cassini's instruments detected what appeared to be a rain of particles falling from Saturn's rings into its atmosphere. a constant gentle precipitation of ice and dust, material from those magnificent structures slowly spiralling inward and becoming part of the planet itself. This phenomenon, which scientists came to call ring rain, had been theorized for years, but Cassini's final measurements provided the clearest evidence yet that it was real and ongoing. The rings of Saturn, which appear so permanent and unchanging when viewed from afar, are gradually falling into the planet, contributing their substance to Saturn's atmosphere one grain at a time. Consider for a moment what this means. The rings that make Saturn the most beautiful planet in our solar system are not eternal. They are temporary, cosmically speaking, structures that are being slowly consumed by the world they orbit. Scientists estimate that at the current rate the rings might be gone in 100 million years or so, perhaps 300 million at the outside. This sounds like an impossibly long time, but Saturn is more than 4 billion years old. If the planet's lifetime were compressed into a single year, the rings might endure for only a week or two of that year, perhaps a month. They are, in a sense, a lucky accident of timing. We happen to exist during the brief cosmic moment when Saturn wears its magnificent jewellery. Earlier civilizations might have looked up at a ringless Saturn. Future ones, millions of years hence, almost certainly will. Cassini gave us this knowledge in its final breath, a gift wrapped in fire. It is worth pausing on the strangeness of those 93 seconds, the time between when Cassini entered Saturn's atmosphere and when its signal went silent. In that brief window, less than 2 minutes, shorter than a coffee break, barely enough time to listen to a favourite song, the spacecraft compressed years of potential discovery into a single sustained transmission. Every measurement mattered, every data point was irreplaceable. The scientists back on Earth knew that they would never have another opportunity to sample Saturn's atmosphere directly, not in their lifetimes, not in their children's lifetimes, perhaps not for generations. And so they designed the final plunge with extraordinary care, optimizing every aspect of Cassini's descent to maximize the scientific return. The spacecraft was oriented with its instruments facing into the oncoming atmosphere, its antenna pointed steadfastly toward Earth, its thrusters ready to compensate for the growing aerodynamic forces that threatened to tumble it off course. Everything had to work perfectly, and it did, right up until the moment when the forces became too great and the laws of physics finally prevailed. One of the most poignant details of Cassini's end is how hard it fought to keep talking. The spacecraft's thrusters fired continuously during the descent, making constant tiny adjustments to keep that high-gain antenna pointed at Earth. It was a losing battle. The atmosphere was growing denser by the second, the drag on the spacecraft increasing, the forces pushing against the antenna becoming stronger and stronger. But Cassini kept fighting, kept adjusting, kept transmitting, right up until the very last moment. When the signal finally cut off, it did so cleanly. There was no gradual fade, no static, no desperate last gasp. One moment Cassini was there, sending its measurements, sharing what it was experiencing. The next moment, it was gone. The engineers monitoring the transmission said it was like a light being switched off. Sharp, definitive, final. In the silence that followed, Saturn continued to turn. Return with me, one more time, to the question of why. Why destroy a spacecraft that was still working perfectly? Why deliberately end a mission that could have continued gathering data for months, perhaps years? The fuel was running low, yes, but Cassini's instruments were functioning beautifully, and there might have been ways to extend the mission just a little longer, to squeeze out a few more observations, to delay the inevitable. The answer, as we have seen, was protection. But now that we understand more about Enceladus and Titan, about the oceans hidden beneath their ice, about the geysers spraying water into space, about the complex organic molecules that Cassini itself discovered, we can appreciate just how serious that protection mandate was. Imagine if Cassini had been allowed to run completely out of fuel, to tumble uncontrolled through the Saturn system, its trajectory no longer predictable. Imagine if, centuries or millennia from now, that dead spacecraft had drifted into the gravitational grip of Enceladus, had spiraled slowly down through the plumes erupting from its south pole, had crashed into that moon's icy surface. And imagine if, clinging to Cassini's structure, there were still microorganisms from Earth, hardy bacteria that had survived 2 decades in space, dormant but alive, waiting. If those microbes reached Enceladus's subsurface ocean, if they found a way to survive in that warm, chemical-rich environment, the consequences would be both scientifically catastrophic and philosophically troubling. We would never know whether life we discovered there was native to that world or carried from our own. We would have compromised one of the most precious questions in all of science. Are we alone? Through carelessness and impatience. The scientists who decided to end Cassini understood this. They understood that protecting the possibility of discovery was more important than extending the mission. They understood that some knowledge is so valuable that we must sacrifice other knowledge to preserve the chance of finding it. And so they chose, with heavy hearts, to kill their spacecraft rather than risk contaminating worlds that might harbour life. There is something noble in that choice, something that speaks to the best of what humanity can be. We are not always good stewards of our planet, not always careful with the fragile things in our care. But in this case, confronted with the possibility of life on another world, we chose to be responsible. We chose to be humble. We chose to put the question ahead of the answer, the mystery ahead of our own curiosity. Spare a thought, too, for the people who made that choice, who had to decide deliberately and with full awareness of what they were doing to end something they had nurtured for 20 years. It is one thing to lose a spacecraft to equipment failure, to a failed rocket, to the random cruelty of the universe. That kind of loss is tragic, but it is not chosen. The loss of Cassini was different. Every engineer, every scientist, every member of the team knew exactly what they were doing. They sent the final commands, they pointed the spacecraft towards Saturn, they watched as it began its last descent, and then they sat together in a room in Pasadena and listened as the signal faded and stopped. Consider for a moment what that must have felt like, to have spent years of your life building, launching and operating a machine, growing to know its quirks and strengths, celebrating its discoveries, worrying when things went wrong, taking pride when they went right, and then to deliberately destroy it, to send it to its death, to choose the moment of its ending. The engineers described Cassini with language usually reserved for people. They called it brave, faithful, tireless. They mourned it as if it were a colleague, and perhaps in a way it was. Let us sit for a long moment with the idea of what Cassini left behind, not the physical debris, which dispersed into Saturn's winds and became part of the planet, individual atoms of carbon and aluminum and gold, mixed now and forever with the hydrogen and helium of that vast world. Not that, though, there is something beautiful in the thought of a spacecraft becoming part of the planet it studied, its substance merging with the world it loved. What Cassini left behind was knowledge. Over the course of its mission, the spacecraft sent back nearly 500,000 images, enough to fill libraries with wonder. It made discoveries about Saturn's rings that rewrote our understanding of how such structures form and evolve. It mapped Titan's surface, revealing lakes of liquid methane and dunes of organic particles. It detected the geysers of Enceladus and traced their source to a hidden ocean. It observed storms and auroras and magnetic fields, watched seasons change on a world where a single year lasts 30 Earth years, measured temperatures and pressures and densities. All of this knowledge, every image, every measurement, every discovery, travelled across more than 800 million miles of space to reach us. It arrived as radio waves, invisible ripples in the electromagnetic field, carrying information encoded in ones and zeros. The journey took about an hour and a half. The timelight itself needs to cross that immense distance. And when the signals arrived at Earth, they were almost unimaginably faint, weaker than the warmth of a candle a mile away, fainter than almost anything the human instruments could detect. That we can receive such signals at all is one of the quiet miracles of our age. That we can build machines to generate them, send them across the solar system, and interpret them correctly upon arrival. This represents a triumph of human ingenuity and cooperation that we too often take for granted. Every image from Cassini was a message in a bottle, cast into the cosmic ocean, and somehow, against all odds, reaching its destination. There is one more thing worth understanding about the days following Cassini's end, a detail that captures something essential about how science works and why it matters. When the final data from Cassini's plunge arrived at Earth, the scientists did not simply look at it and announce their conclusions. That is not how the process works. Instead, they began the slow, careful work of analysis, comparing measurements to models, checking for errors, trying to understand what they were seeing. The data was surprising, and surprising data demands extra scrutiny. Had the instruments malfunctioned? Were there calibration issues? Was there some explanation for these unexpected findings that did not require revising the textbooks? This process took months. The scientists worked through the data systematically, ruling out alternative explanations one by one, building confidence in their results. When they finally published their findings nearly a year after Cassini's death, they did so with the full weight of that careful analysis behind them. The discoveries were real, the surprises were genuine. Saturn's atmosphere was more complex than anyone had expected, and the ring rain was falling just as the models had tentatively predicted. This is how knowledge accumulates, not in dramatic revelations, but in patient work. The final seconds of Cassini's existence generated data that took a year to interpret, and the interpretation will continue for years more. Scientists are still working through the archive of Cassini's observations, finding new patterns, answering old questions, raising new ones. A mission that ended on a September morning in 2017 continues to teach us things today, and will continue to teach us for decades to come. Picture, if you can, what Saturn looks like tonight. It is out there somewhere in the darkness, orbiting the Sun as it has for billions of years, its great rings catching the faint light and reflecting it back into space. Those rings are still falling, grain by grain, into the planet's atmosphere, still participating in that slow cosmic rain that Cassini detected in its final moments. The geysers of Enceladus are still erupting, spraying water ice into the darkness, contributing fresh material to Saturn's faint outer ring. Titan is still shrouded in its orange haze, hiding its lakes and mountains and alien coastlines from our view. And somewhere in Saturn's atmosphere, diffused now, scattered beyond any hope of recovery, are the atoms that once were Cassini. Carbon from the spacecraft's body, copper from its wires, silicon from its circuits, gold from its thermal blankets. These particles have become part of Saturn, mixed into the winds and clouds of that great world, carried by currents we cannot see to depths we cannot reach. In a sense, Cassini has achieved a kind of immortality, though not the kind we usually imagine. It will never broadcast another image, never take another measurement, never surprise us with another discovery. But its substance endures, woven into the fabric of the planet it studied. Every time Saturn rises in our night sky, a tiny fraction of what we see is Cassini, transformed, unrecognizable but present, and we, looking up at that golden point of light, carry something of Cassini within us as well. Not atoms or molecules, but something perhaps more enduring, understanding. We know things about Saturn that we did not know before, things that no human being could have known a generation ago, things that exist in our minds only because a small spacecraft spent 2 decades flying through darkness and sending back what it found. This is the true legacy of exploration, not the hardware, which eventually fails, and not the data, which eventually becomes obsolete, but the expansion of human understanding. The things we learn become part of us, part of our culture, part of our collective knowledge. They are passed from generation to generation, refined and extended, becoming the foundation for discoveries not yet made. There is something profound in this, something worth holding close as you lie in the darkness and think about distant worlds. The universe is vast and cold and utterly indifferent to human concerns, and yet here we are, small and warm and curious, sending our mechanical emissaries into the void, learning what we can, adding to the sum of human knowledge one measurement at a time. This is not nothing. This is perhaps everything. It is worth trying, just once, to feel what the Saturn system must be like in the absence of Cassini. The spacecraft had been a constant presence for 13 years, looping through that miniature solar system, passing close to moons and rings, photographing everything it could see. Its instruments listened to radio waves and measured magnetic fields. Its cameras captured images that humans had never seen before and may never see again. For more than a decade, Saturn had a mechanical companion, something watching, something paying attention, something reporting back to the small blue world in the inner solar system where the watchers waited. Now that companion is gone. The Saturn system continues exactly as it did before, unchanged by the presence or absence of observers. The rings turn, the moon's orbit, the storms swirl in the atmosphere. But there is no one there to see it, no one to record it, no one to translate its beauty into images and data and understanding. When we send a spacecraft to another world, we extend our senses across the gulf of space. We see through its cameras, we feel through its instruments, we touch, in a mediated but real way, surfaces and atmospheres that our bodies could never reach. And when that spacecraft dies, we become blind again. The world continues, but our window closes. This is why the loss of Cassini felt to many people like the loss of something precious. It was not just a machine that stopped functioning. It was a way of seeing that ended. For 13 years, humanity had eyes at Saturn. Now we do not. The next mission to that distant world, if it comes at all, is decades away. An entire generation will grow up without new images from the ringed planet, without fresh discoveries from its moons, without the particular wonder of seeing something no one has ever seen before. And so we must content ourselves, for now, with what Cassini gave us. 500,000 images, countless measurements, discoveries that changed our understanding of the solar system, the knowledge that Enceladus might harbour life, that Titan has lakes, that the rings are raining into the atmosphere, that Saturn's winds blow faster than any hurricane on Earth. These gifts remain, even though the giver is gone. Return with me, one final time, to the control room at the Jet Propulsion Laboratory on that September morning. The screens have gone dark. The telemetry has stopped. The spacecraft that had been a constant presence for 2 decades exists now only in memory and in the archive of data it left behind. The engineers and scientists sit quietly, some wiping tears from their eyes, others staring at displays that show nothing. Someone, perhaps unconsciously, reaches out and touches a console, as if trying to establish contact with something that can no longer respond. There is talk, eventually, reminiscences about the mission, memories of triumphs and close calls, gratitude for having been part of something so remarkable. But for a long moment, there is only silence. In that silence, Saturn continues to turn, 800 million miles away. The planet does not know that its observer has departed, does not feel the absence of the small machine that had been its companion for so long. The storms continue to swirl, the rings continue to spin, the moons continue their ancient dance, and on Earth, a group of humans sit together in a room in California, mourning a spacecraft, celebrating a mission, and beginning the long process of understanding everything that Cassini taught them in its final moments of life. The data that Cassini transmitted during those last 93 minutes would take years to fully analyse. Even now, scientists continue to find surprises buried in the measurements, small revelations that emerge only after careful study and comparison with everything else the spacecraft had gathered during its long mission. But some of the discoveries were apparent almost immediately, emerging from the raw data like shapes rising out of fog. Consider, for a moment, the question of Saturn's magnetic field. Before Cassini's grand finale, scientists believed they understood its basic structure. Saturn, like Jupiter and Earth, generates a powerful magnetic field through the churning of conducting fluids deep within its interior. This field extends far out into space, creating a vast protective bubble that deflects the solar wind and traps charged particles in radiation belts. But there was something strange about Saturn's field, something that had puzzled researchers for decades. On every other planet with a global magnetic field, the field is tilted, offset from the planet's rotational axis by at least a few degrees. Earth's magnetic poles, for instance, do not align perfectly with its geographic poles. Jupiter's field is tilted by about 10 degrees. Even the fields of Uranus and Neptune are dramatically skewed. But Saturn's field, according to every measurement taken before the grand finale, appeared to be perfectly aligned with its rotation axis. The tilt was effectively zero, within the precision of the measurements. This was deeply strange, because the theories that explained how planetary magnetic fields are generated seemed to require some asymmetry, some tilt to work properly. A perfectly aligned field should not, according to those theories, be able to sustain itself over time, and yet Saturn appeared to have exactly that, a magnetic field that should have been impossible. During the grand finale orbits, Cassini carried its magnetometer closer to Saturn than any instrument had ever been. It measured the field with exquisite precision as it dove between the rings and the atmosphere, sampling conditions that no one had ever sampled before, and what it found surprised everyone. The field was still almost perfectly aligned. The tilt was less than 1 degree, smaller than any other known planetary field. But the data revealed something else, something unexpected. The magnetic field was different at different latitudes, varying in ways that the older, more distant measurements had not been able to detect. There were structures in the field, patterns that hinted at complex processes occurring deep within Saturn's interior. The simple, smooth, symmetric picture that scientists had constructed was replaced by something richer and more mysterious. The field was still remarkably aligned, still defying theoretical expectations, but now it was also clearly more complicated than anyone had assumed. Cassini had died before it could fully explain what it had found, but it had revealed that our understanding of Saturn's magnetic interior was incomplete in ways we had not even suspected. And there was another puzzle, one that had nagged at scientists for decades. No one knew exactly how fast Saturn was rotating. This might seem like a simple thing to measure. Just watch the planet turn and time how long it takes for a feature to come back around. But Saturn's atmosphere is fluid, swirling with winds and storms that move at different speeds at different latitudes. There are no fixed landmarks on its surface, no craters or mountains to track. The clouds race around the planet at hundreds of miles per hour, their motion telling you more about the winds than about the underlying rotation of the planet itself. Scientists had tried to use radio signals from Saturn's magnetosphere to determine the rotation rate, assuming that the magnetic field was anchored to the deep interior and would reveal the planet's true spin. But the signals varied in puzzling ways, giving different answers at different times. The rotation period of Saturn's interior remained stubbornly uncertain, a basic fact about the planet that no one could pin down. Cassini's final measurements helped to clarify this mystery, though they did not entirely solve it. The spacecraft's close passes through the magnetic field provided new data on how the field changed with time and position, giving scientists better tools for untangling the rotation signal from the noise of atmospheric and magnetospheric variability. The emerging picture suggested that Saturn's deep interior rotated about once every 10 hours and 33 minutes, faster than some earlier estimates, slower than others, and still carrying significant uncertainty. But the data also revealed that the situation was even more complicated than a simple rotation period could capture. Saturn's interior appeared to be rotating differentially, with different layers spinning at slightly different rates. The planet was not a rigid ball, but a complex layered system where the concept of a single rotation period might not even apply in the simple way it does for Earth. Once again, Cassini had answered a question by revealing that the question itself was more subtle than anyone had realized. It is worth pausing on how strange this is, that we could send a spacecraft to orbit a planet for 13 years, measure it from every angle with the most sophisticated instruments we could build, and still not know something as basic as how fast it spins. This is the nature of scientific exploration. Every answer opens new questions. Every measurement reveals the limits of our previous understanding. The universe is not a puzzle that we are close to completing. It is an infinite tapestry that becomes more intricate the closer we look. Spare a thought, too, for the question of Saturn's internal structure. Before Cassini's grand finale, scientists had constructed models of what lay beneath the planet's clouds, models based on theoretical calculations, laboratory experiments, and distant observations. Saturn, they believed, consisted of layers. At the centre, a core of rock and ice, perhaps 10 to 20 times the mass of the Earth, compressed by the enormous weight of everything above it. Surrounding this core, a thick shell of metallic hydrogen, the element squeezed to such high pressures that its electrons broke free and it began conducting electricity like a metal. Above that, a deep ocean of liquid hydrogen and helium, transitioning gradually into the gaseous atmosphere that we see from space. This layered structure was thought to explain Saturn's relatively low density, its powerful magnetic field, and the heat that the planet radiates into space. But no one had directly measured what lay beneath the clouds. The models were educated guesses, constrained by what we knew but not confirmed by direct evidence. During the grand finale, Cassini's trajectory through Saturn's gravitational field provided a new way to probe the planet's interior. As the spacecraft fell toward the planet and climbed back out, Saturn's gravity tugged on it in ways that depended on exactly how mass was distributed inside the planet. By tracking Cassini's velocity with exquisite precision, using radio signals bounced between the spacecraft and Earth, scientists could measure tiny variations in the gravitational pull. These variations, in turn, revealed information about the density structure deep below the clouds. What the data showed was, once again, surprising. The core of Saturn appeared to be larger and more diffuse than the models had predicted. Rather than a compact, well-defined ball of rock and ice at the centre, Saturn seemed to have a core that was spread out, mixed with the surrounding hydrogen and helium to a greater extent than expected. The boundary between the core and the envelope above it was fuzzy, indistinct, a gradual transition rather than a sharp edge. This finding had implications for how Saturn formed, how it has evolved over the billions of years since its birth, and how giant planets in general develop their internal structures. The simple layered picture, while not wrong in its broad strokes, needed to be complicated. Saturn's interior was more mixed, more dynamic, more surprising than the models had suggested. And then there was the matter of how much material was falling from the rings into the atmosphere. Scientists had suspected that the rings were raining down onto Saturn, that tiny particles of ice and dust were spiralling inward under the influence of gravity and other forces, eventually entering the atmosphere and being absorbed. But no one knew how fast this was happening, how much material was being transferred, or what effect it might have on the planet over time. Cassini's final orbits carried it directly through this rain. The spacecraft's instruments detected particles striking its sensitive surfaces, measuring their mass and velocity. What they found was that the ring rain was far more intense than anyone had expected. Thousands of kilograms of material were falling into Saturn every second, mostly water ice from the rings, but also more complex organic compounds and silicate particles. The rings were losing mass at a rate that would, if it continued unchanged, cause them to disappear entirely in a few 100 million years. This was, in cosmic terms, a very short time, far shorter than the age of the solar system. It raised the startling possibility that Saturn's rings might be relatively young, perhaps formed only 100 million years ago or so, long after the dinosaurs first appeared on Earth. If this were true, then the rings that seemed so permanent, so defining of Saturn's character, might be a temporary feature, a passing decoration rather than an eternal companion. This finding, emerging from data gathered in Cassini's final hours, sparked intense debate among planetary scientists. Not everyone agreed with the interpretation. Some argued that the ring rain rate might have been enhanced during the grand finale period, that the spacecraft's measurements might not represent the long-term average. Others pointed out that the rings could be continuously replenished by material from comets or the disruption of small moons, maintaining themselves even as they lose mass to the atmosphere. The question of the ring's age remains open, a mystery that Cassini illuminated but did not fully solve. What is certain is that the final data revealed the rings to be dynamic, evolving, exchanging material with Saturn in ways that were far more active than anyone had previously understood. Return with me, one more time, to that cascade of measurements streaming back to Earth in those final 93 minutes. Picture the data flowing through space, carried by radio waves at the speed of light, crossing the vast emptiness between Saturn and Earth in 83 minutes. By the time the signals arrived at the Deep Space Network antennas in Australia, Cassini was already gone. The spacecraft that had sent them no longer existed. Destroyed in the very act of gathering these final observations, there is something poignant in this temporal delay, this gap between the moment of measurement and the moment of reception. The Cassini that transmitted those signals was still alive, still functioning, still doing its job. But the Earth that received them was an Earth from which Cassini had already departed. The spacecraft and the scientists were never truly in the same moment, separated not just by distance but by time. Consider for a long moment what it must have been like to be one of those scientists standing in the control room, watching the data arrive knowing that the sender was already dead. Every measurement was a gift from the past, a message from a spacecraft that no longer existed. The numbers on the screen represented conditions that had been measured 83 minutes ago, temperatures and pressures and magnetic fields that Cassini had sampled in its final moments of awareness. By the time human eyes saw those numbers, the spacecraft had long since been torn apart, compressed, heated, vaporized, and dispersed through Saturn's atmosphere. The data was all that remained. The digital ghost of a machine that had spent 2 decades in space, that had travelled billions of miles, that had transformed our understanding of another world. And the data was beautiful. Even in those compressed final moments, as the spacecraft struggled against thickening atmosphere and mounting heat, the instruments continued to function, continued to measure, continued to transmit. The mass spectrometer detected molecules that had never been directly sampled before, giving scientists their first direct taste of Saturn's atmosphere at depths where no instrument had ever reached. The magnetometer recorded field structures that refined our understanding of the planet's interior. The radio link maintained contact until the very end, its signal weakening and distorting but never quite giving up. Cassini died doing exactly what it was built to do, gathering data until the laws of physics finally made it impossible to continue. There is one more thing worth understanding about what Cassini's death revealed. In the weeks and months following September 15th, 2017, scientists began to piece together a more complete picture of how the spacecraft had died. They knew from the telemetry exactly when the signal had been lost. They knew from the engineering models approximately what had happened in those final seconds. But the detailed reconstruction of Cassini's death, informed by all the data gathered during the grand finale, told a story that was both technical and strangely moving. The spacecraft had entered Saturn's atmosphere travelling at more than 75,000 miles per hour relative to the swirling clouds. At that speed, the air, if you can call the mixture of hydrogen and helium that makes up Saturn's atmosphere air, offered tremendous resistance. Cassini began to heat up, its surfaces warming as the energy of its motion was converted into heat through friction and compression. The spacecraft was never designed to be a heat shield. It had no protective tiles, no ablative coating, no systems meant to survive atmospheric entry. It was a scientific instrument, built for the vacuum of space, now plunging into an environment that would have been hostile to almost any machine humans could build. For a few seconds, the attitude control system fought to keep Cassini oriented correctly. The thrusters fired, struggling to counteract the aerodynamic forces that were pushing the spacecraft off course. The flight software worked exactly as designed, doing everything possible to maintain the proper pointing for the antenna, to keep the high-gain dish aimed at Earth, to ensure that every last bit of data could be transmitted. This was the spacecraft's final act of faithfulness, not surrendering to the forces tearing it apart, but fighting to complete its mission until the very end. The thrusters ran out of fuel, or perhaps the aerodynamic forces simply became too strong. The telemetry shows that Cassini began to tumble, losing its stable orientation, spinning away from the configuration it had maintained for 2 decades. The high-gain antenna swung away from Earth. The signal, which had been growing weaker as the atmosphere absorbed the radio waves, finally cut off entirely. On Earth, 83 minutes later, the engineers saw the carrier signal vanish from their displays. They knew what this meant. The spacecraft that had been their constant companion for 20 years was gone. What happened next is a matter of physics rather than telemetry, because there was no more telemetry to receive. The spacecraft continued to fall, tumbling through ever thicker atmosphere, heating more intensely with every passing second. The temperatures exceeded the melting points of its components. The delicate instruments that had gathered so much data began to fail and deform. The fuel tanks ruptured, the structure broke apart. Within a few minutes, what had been Cassini was now a cloud of hot gas and vapour, mixed with fragments of metal and ceramic, dispersing through Saturn's atmosphere and becoming finally part of the planet it had studied for so long. There is a strange and beautiful symmetry in this ending. The atoms that made up Cassini, the aluminum and titanium and gold, the silicon and carbon and exotic alloys, were forged billions of years ago in the hearts of ancient stars. They had spent their time on Earth, been refined and shaped by human hands, launched into space, and carried across billions of miles to orbit a distant world. And now they had returned to the interior of a giant planet, joining the vast reservoir of material that makes up Saturn, becoming part of the world they had been sent to study. In a very real sense, Cassini did not die. It transformed. The matter and energy that constituted the spacecraft were not destroyed, but rearranged, dispersed, incorporated into something much larger than any spacecraft could ever be. Picture, if you can, what those atoms are doing now. The metals that were once structural beams and electronic components are scattered through Saturn's upper atmosphere, sinking slowly deeper as they interact with the surrounding gases. In 100 years, in 1,000 years, they will have mixed so thoroughly that no trace of their origin remains, just a few trillion extra atoms of unfamiliar elements, diluted beyond detection in the ocean of hydrogen and helium that makes up most of the planet. The spacecraft has become part of Saturn, woven into the fabric of the world it was sent to understand. Let us sit for a long moment with what this means. When we send missions to other worlds, we speak of exploration, of discovery, of extending human presence across the solar system. But we do not often speak of what happens when those missions end, when the spacecraft that carried our hopes and our instruments finally stops functioning. Most of the machines we have sent to space are still out there somewhere, drifting in orbit or resting on distant surfaces, silent monuments to human curiosity. But Cassini became something different. It became part of the world it studied. It joined Saturn in a way that no human and no other machine ever has. This was, in a sense, the final gift of the mission. Not just the data gathered in those last 93 minutes, but the symbolic completion of a journey that had begun with a question. We asked what Saturn was like, what its moons held, what its rings were made of, what secrets it kept hidden beneath its clouds. And in answering those questions, Cassini gave everything it had, until there was nothing left to give, and then gave itself entirely to the world it had come to know. The scientists who designed the grand finale understood this symbolism. They did not speak of crashing Cassini or destroying it or disposing of it. They spoke of the spacecraft becoming part of the planet it studied. This language was deliberate, chosen to honour the mission and the machine that carried it out. There is no gravestone for Cassini, no marker to indicate where it fell, no way to point at a spot in Saturn's atmosphere and say, there it rests. The spacecraft is everywhere and nowhere now, its substance distributed through the upper layers of a world 800 million miles from where it was built. But perhaps that is the most fitting memorial possible. Not a fixed monument, but a final transformation, a machine that became indistinguishable from its subject. And we cannot leave this story without acknowledging what Cassini's death protected. The decision to send the spacecraft into Saturn was not made lightly, and it was not made for symbolic reasons alone. The primary motivation was scientific and ethical, the protection of worlds that might harbour life. Enceladus, with its subsurface ocean and its geysers venting potential nutrients into space. Titan, with its complex organic chemistry and its liquid hydrocarbons. These moons, revealed by Cassini to be far more interesting and potentially more habitable than anyone had expected, needed to be protected from contamination by an uncontrolled spacecraft. Cassini had been in space for 20 years, but it had been built on Earth, assembled by human hands in rooms that, despite the best efforts of engineers, were not perfectly sterile. The spacecraft carried hitchhikers, microorganisms, spores, perhaps even hardy bacteria that could survive the vacuum of space and the radiation environment around Saturn. As long as the spacecraft was functioning, under control, this was not a concern. The mission team could ensure that Cassini never collided with Enceladus or Titan, never deposited its microscopic cargo on surfaces where life might already exist or might someday arise. But no spacecraft functions forever. Eventually Cassini's fuel would run out, its thrusters would fall silent, its ability to maneuver would end, and then it would become a drifting derelict, following whatever orbit it happened to be in, subject to the gravitational tugs and pulls of Saturn and its moons over thousands and millions of years. Computer simulations showed that, given enough time, an uncontrolled Cassini would eventually collide with one of the moons. Perhaps Titan, perhaps Enceladus. And when it did, it might carry with it the seeds of Earth life, contaminating a pristine world, confusing future searches for native biology, perhaps even, if the contamination took hold, destroying whatever indigenous life might have existed there. This was a risk that the planetary science community found unacceptable. The same spirit of exploration that had driven the mission from the beginning demanded that we not spoil the very worlds we had come to study. And so the decision was made, years before the grand finale began, that Cassini would end its mission in a controlled way, plunging into Saturn where no life could possibly exist, where the intense heat and pressure would sterilize any hitchhikers beyond any possibility of survival. The spacecraft would be destroyed, but the moons would be protected. The exploration would end, but the integrity of the unexplored would be preserved. There is something deeply ethical in this choice, a recognition that our hunger to know must be balanced against our responsibility to protect. We sent Cassini to Saturn to learn, and we destroyed Cassini to ensure that what we learned was true, that when future missions search for life on Enceladus or Titan, they will find what is actually there, not the descendants of bacteria that hitchhiked from Earth on a spacecraft that crashed centuries before. The death of Cassini was an act of scientific discipline, a sacrifice made in service of knowledge we do not yet possess, protecting discoveries that we have not yet made for scientists who have not yet been born. And in this sacrifice we find perhaps the clearest expression of what separates exploration from conquest, what distinguishes science from mere acquisition. We went to Saturn not to claim it, but to understand it. And when the time came, we chose to let our emissary dissolve into the very atmosphere it had studied for 13 years, rather than risk harming the worlds we had grown to love. This is a kind of maturity, a coming of age for our species as explorers. We are learning, slowly, that the universe is not ours to spoil. But let us return, one more time, to those final hours and to what Cassini found as it fell. The spacecraft's instruments remained active far longer than many had expected, continuing to gather data as the atmosphere thickened around it, as pressures rose and temperatures climbed, as the craft began to experience conditions that no human-made object had ever encountered before. The ion and neutral mass spectrometer, which had spent years analysing the particles in Saturn's rings and the plumes of Enceladus, now turned its attention to the atmosphere itself, sampling the gases that swirled around the descending probe. What it found in those final minutes would take scientists years to fully analyse, and some of the results would prove genuinely surprising. The helium abundance, for instance. Saturn is composed almost entirely of hydrogen and helium, the simplest elements, the primordial stuff left over from the Big Bang. But the ratio of these two gases in Saturn's atmosphere had been a matter of some uncertainty. Cassini's final measurements suggested that helium was less abundant in Saturn's upper atmosphere than models had predicted, a finding that has implications for our understanding of how giant planets evolve over billions of years. Deep within Saturn, under pressures that crush matter into exotic states, helium may be slowly separating from hydrogen, sinking toward the planet's core like rain falling through an alien ocean of metallic hydrogen. This helium rain, if it exists, would release energy as it falls, helping to explain why Saturn radiates more heat than it receives from the Sun. Cassini's final breaths helped confirm this possibility, adding a crucial data point to a mystery that stretches back decades. The spacecraft also detected organic molecules in Saturn's atmosphere, complex compounds containing carbon and hydrogen, the building blocks of the chemistry that, on Earth, leads to life. These molecules were not evidence of life. Saturn's crushing pressures and extreme temperatures make the planet itself thoroughly inhospitable. But they were evidence of the rich chemistry that pervades the outer solar system, the same kind of chemistry that makes Titan's atmosphere so fascinating and that may, in the hidden oceans of Enceladus, be cooking up possibilities that we cannot yet imagine. Even in its final moments, Cassini was finding connections, weaving together the threads of a larger story about how complex chemistry arises in the cosmos. And then there was the magnetic field data, some of the most puzzling measurements of the entire mission. Saturn's magnetic field had always been a mystery. Unlike Jupiter, whose magnetic field is tilted relative to its rotation axis, Saturn's field appeared to be almost perfectly aligned, the magnetic poles nearly coinciding with the geographic poles, the axis of the field nearly parallel to the axis of rotation. This was strange, because the theories that explain how planets generate magnetic fields suggested that such perfect alignment should be impossible. There should have been some tilt, some offset, some deviation from perfection. Cassini's grand finale orbits, diving closer to Saturn than any previous spacecraft, had been designed in part to investigate this mystery, and the final plunge provided the closest measurements of all. What the magnetometer found was that Saturn's field was even more perfectly aligned than anyone had thought. The tilt, if it existed at all, was smaller than measurement uncertainties could detect. This was a genuine surprise, a result that sent theorists back to their equations, searching for explanations of how a planet could generate a magnetic field with such impossible symmetry. Some have suggested that Saturn's field might have a slight tilt that is hidden by the planet's atmosphere, that currents flowing in the outer layers of Saturn might be somehow cancelling out the tilt, presenting an illusion of perfect alignment. Others have proposed more radical ideas, suggesting that our understanding of how magnetic fields are generated in giant planets might need revision. The mystery remains unsolved. One more question that Cassini bequeathed to future scientists, one more reason why we must eventually return. Consider, for a moment, what it means that a spacecraft could send back such surprising data in its final minutes of existence. The mission had lasted for 20 years, from launch to fiery end. It had revolutionized our understanding of the Saturn system, discovered new moons, revealed geysers and hidden oceans, provided evidence that life might exist in places we never expected. And yet, even at the very end, even as it tumbled toward destruction, it was still finding things that surprised us, still overturning expectations, still reminding us how much we have yet to learn. This is the nature of exploration. The deeper we look, the more we find. Every answer opens new questions. Every discovery reveals new mysteries. We sent Cassini to Saturn thinking we knew roughly what to expect, and it spent 13 years showing us how wrong we were, how limited our imaginations had been, how much more complex and wonderful the universe is than we had dared to suppose. It is worth pausing on the human element of those final transmissions, the people who received them, and what they experienced in that control room as the signal faded. The Deep Space Network antenna in Canberra, Australia, was the one that captured Cassini's last words. It was morning there, the southern hemisphere's spring, while much of the mission team gathered in California where it was still the dark hours before dawn. The signals, travelling at the speed of light, took over an hour to cross the void between Saturn and Earth. By the time the first data from the final plunge arrived, Cassini had already been gone for 83 minutes, already transformed from spacecraft to atmosphere, from machine to molecules. The team watched numbers scroll across screens, watching the data rate, watching the signal strength, watching the instruments report their findings from a world nearly 1 billion miles away. And then, at 7:55 a.m. Eastern Time on September 15th, 2017, the signal stopped. It didn't fade slowly. It didn't weaken and waver. It simply ended, as if someone had thrown a switch. One moment there was data, and the next there was silence. The spacecraft had tumbled. The antenna had lost lock with Earth. And in that same instant, or perhaps milliseconds later, Cassini had begun to break apart, its components separating, its propellants vaporizing, its structure heating and fragmenting and finally dissolving into the clouds. In the control room, there were tears. Engineers who had worked on the mission for decades, scientists who had devoted their careers to analysing its data, managers who had shepherded it through countless challenges. They wept for a spacecraft, for a mission, for an era that had ended. Julie Webster, the spacecraft operations team manager, later described the moment as bittersweet but actually more sweet. Earl Mays, the project manager, called it the final breath of a friend. These were not sentimental exaggerations. 20 years is a long time, long enough for relationships to deepen, for affection to grow, for a machine to become, in some real sense, a companion. And we cannot leave this story without acknowledging the children who grew up with Cassini. There are scientists working on the data today who were in elementary school when the spacecraft launched, who grew up watching its images on television and on early websites, who chose their careers in part because of what Cassini showed them was possible. The mission has become a teaching tool, an inspiration, a proof that difficult things can be accomplished if we are patient and persistent and willing to work together across borders and across decades. When those children, now adults, now scientists themselves, examine the data from Cassini's final plunge, they are completing a circle that began before many of them could read. Return with me, one more time, to the rings. Throughout its mission, Cassini had studied Saturn's rings in unprecedented detail, revealing them to be not the simple, stable structures they appeared to be from Earth, but dynamic, ever-changing phenomena, full of waves and ripples and patterns created by the gravitational influence of Saturn's many moons. The spacecraft had discovered new ringlets and new gaps, had watched as moons embedded within the rings created wakes and disturbances, had seen the rings in ways that no human eye had ever seen them before. And in those final months during the grand finale orbits, Cassini made a discovery that surprised everyone. The rings were raining onto Saturn. This was not entirely unexpected. Scientists had theorized for decades that Saturn's rings might be slowly losing material to the planet below, but the rate of this ring rain, as measured by Cassini, was far higher than anyone had predicted. Material was falling from the rings into Saturn's atmosphere at a rate that suggested the rings might be disappearing, slowly but surely, evaporating into the planet they encircle. In perhaps 100 million years, a blink in cosmic time, the rings might be gone entirely, leaving Saturn as bare as Jupiter or Neptune. This was a humbling discovery. We tend to think of the solar system as fixed and eternal, its features as permanent as mountains. But Cassini showed us that even Saturn's magnificent rings are temporary, a passing phenomenon, a cosmic snowfall that will eventually end. We happen to live in an era when Saturn has rings. Future civilizations, millions of years hence, may look up at a Saturn as plain and unadorned as any other gas giant, and they will have to take our word for it that rings once existed. Spare a thought too for the sounds of Saturn that Cassini captured. Not literal sounds, of course, for space is silent, but radio emissions that scientists converted into audio, allowing human ears to experience something of the electromagnetic environment around the ringed planet. These sounds are strange and beautiful, whistles and hisses and whoops that seem almost like whale song, almost like music, almost like a language we cannot understand. The spacecraft recorded these emissions throughout its mission, and some of the most haunting recordings come from the final orbits, as Cassini passed through regions it had never explored before, hearing frequencies it had never encountered. When you listen to these recordings, and you can find them easily, archived by NASA and available to anyone with an internet connection, you're hearing the voice of a world that no human will visit for generations, perhaps centuries. You're hearing radio waves converted to sound waves, electromagnetic vibrations transformed into the vibrations of air. You're hearing Saturn sing, and you're hearing it through the ears of a spacecraft that is now part of the planet itself. There is something circular in this, something poetic. The messenger has become the message, the listener has become the sound. Picture, if you can, what the final moments looked like from Cassini's perspective. If a spacecraft can be said to have a perspective, if we can permit ourselves this small act of imagination without pretending that the craft was conscious or afraid. The camera was pointed towards Saturn, capturing images of the atmosphere rushing up to meet it. The clouds below, amber and gold and brown, growing larger and more distinct with each passing second. The curve of the horizon, the vast arc of a world nearly 10 times the diameter of Earth. The faint band of the rings, visible at the edge of the frame, catching the distant light of the sun. And then the images stopped, because there was no longer a camera to take them, no longer an antenna to send them, no longer a spacecraft to carry them home. There was only atmosphere, only chemistry, only the slow incorporation of earthly atoms into a world where they had never belonged. There is one more thing worth understanding about Cassini's death, and it concerns not the spacecraft, but the people who survived it. In the days and weeks after the grand finale, the mission team faced a question that all explorers eventually face. What now? 20 years of purpose had ended. 20 years of daily work, planning orbits, processing data, troubleshooting problems, celebrating discoveries, had come to a sudden stop. For some team members, the end of Cassini was like a bereavement, a loss that took time to process and accept. But for most, the work continued in a different form. The data that Cassini had gathered, over 600 gigabytes of scientific measurements, nearly 500,000 images, thousands of observations of rings and moons and atmosphere, would take years, perhaps decades to fully analyse. The mission may have ended, but the science had only begun. Papers would be written, dissertations would be defended, textbooks would be rewritten. The knowledge that Cassini had gathered would continue to yield discoveries long after the spacecraft itself had become part of Saturn's clouds, and there were new missions to plan. Even before Cassini's final plunge, scientists were proposing follow-up missions to the Saturn system, landers for Titan, probes for Enceladus, spacecraft that could explore the features that Cassini had discovered but could not investigate closely. The Dragonfly mission, a nuclear-powered rotorcraft that will explore Titan's surface in the 2030s, owes its existence in part to what Cassini revealed. Future missions to Enceladus, designed to sample the geysers and search for signs of life, will build on the foundation that Cassini laid. The end of one mission is always the beginning of the next. Let us sit for a long moment with the scale of what was accomplished. A spacecraft was conceived in the 1980s, funded in the 1990s, launched in 1997, arrived at Saturn in 2004, and operated until 2017. It was built by thousands of people across multiple countries, carried instruments designed by dozens of scientific teams, and generated discoveries that touched nearly every branch of planetary science. It transformed our understanding of giant planets, ring systems, icy moons, and the potential for life beyond Earth. It inspired millions of people, young and old, to look up at the night sky and wonder. And when its time came, it was destroyed with dignity and purpose, sacrificing itself to protect the worlds it had helped us understand. This is what humans can do when we work together. This is what we can achieve when we are patient and persistent and willing to invest in ventures that will not pay off for decades. This is the best of us, not the conflicts and cruelties that fill the news, but the quiet, persistent labour of scientists and engineers who spend their lives pushing back the boundaries of the unknown. Cassini is gone now, scattered through the clouds of Saturn, its mission complete, its sacrifice made. But silence is not the same as gone. The data remains, archived and available, waiting to yield new discoveries for generations yet unborn. The images remain, still capable of inspiring wonder in anyone who takes the time to look. The story remains this story, the story of a machine that travelled 1 billion miles and gave us back the solar system in ways we never expected. And Saturn is still there, still turning, still beautiful beyond all description, its rings still catching the light of a sun that seems little more than a bright star from that distance. On some nights, if you go outside and find the right patch of sky, you can see it for yourself, a steady yellowish point of light, brighter than most stars, moving slowly against the background of fixed constellations. You can look at that point of light and know that Cassini is there now, part of the planet itself, its atoms mixed forever with the atmosphere of a world it devoted 13 years to understanding. It is worth trying just once to feel what the mission team felt in those final hours. The pride and the grief, the sense of accomplishment and the sense of loss, the bittersweet knowledge that something beautiful had ended, and that it had ended well. They had done something remarkable, something that will be remembered long after all of them are gone. They had sent a piece of Earth to Saturn and had used it to transform our understanding of the cosmos. And now, in these closing moments, let us return one final time to that September morning, to that room in California where the signal died, and let us stay there a little longer than we have before. The room was quiet in a way that rooms rarely are when they contain so many people. There were perhaps 200 of them gathered there. Scientists, engineers, administrators, journalists, family members of team members who had been invited to witness history. Some had been with the mission since the 1980s, since Cassini was nothing more than an idea sketched on whiteboards and argued over in conference rooms. Others had joined just a few years earlier, young researchers who would carry the mission's legacy forward into the decades ahead. All of them were watching the same screens, the same readouts, the same slowly updating displays that track the spacecraft's vital signs from 1 billion miles away. The telemetry was still coming in, faint but steady. The spacecraft's final transmissions arriving at Earth 76 minutes after Cassini had already ceased to exist. There is something almost unbearable about that delay, if you let yourself dwell on it. The people in that room were listening to the voice of something that was already gone, receiving messages from a messenger that had already delivered its last word and fallen silent. Every beep, every data packet, every confirmation of instrument function was a ghost signal, an echo travelling across the void at the speed of light, carrying news of a world that no longer had anyone to report on it. Earl Mays, the mission's project manager, stood at the front of the room with his headset on, listening to the communications loop that connected the mission control team. His voice was calm and measured as he announced each phase of the final descent, translating the technical readouts into human language for the audience gathered behind him. Atmosphere entry. Thrusters firing at maximum capacity. Spacecraft orientation stable. Loss of signal expected within approximately 1 minute. And then, at 7:55 in the morning Pacific time, the signal wavered and disappeared. The screens that had shown Cassini's steady stream of data went flat. The audio feed that had carried the soft pings of the spacecraft's transmitter fell silent. There was a long pause, and then Mays spoke again, his voice catching just slightly on the words. The signal from the spacecraft is gone, and within the next 45 seconds so will be the spacecraft. I hope you're all as deeply proud of this amazing accomplishment. Congratulations to you all. This has been an incredible mission, an incredible spacecraft, and you're all an incredible team. I'm going to call this the end of mission. And then people were applauding, and some of them were crying, and others were embracing colleagues they had worked beside for years or decades. It was a strange mixture of celebration and mourning, triumph and loss. They had done exactly what they set out to do. They had given Cassini the ending it deserved, and now Cassini was gone. In the weeks and months that followed, the grief softened into something gentler, something closer to gratitude. The mission teams scattered to their various obligations, analysing the final data, writing the final papers, giving the final conference presentations. But there were also quieter rituals, private ceremonies that the public never saw. Some team members kept small mementos from the mission, fragments of test hardware or printed images or mission patches that had travelled with them through the years. Others found themselves returning again and again to the photographs that Cassini had taken in its final days. Those last views of Saturn's clouds, those final glimpses of the rings, that pale blue dot of Earth shining through the ring plane. And there were the letters. In the months after the grand finale, thousands of people from around the world wrote to NASA, expressing what Cassini had meant to them. Children who had grown up watching the mission's discoveries unfold. Teachers who had used Cassini images in their classrooms. Amateur astronomers who had spent years tracking Saturn through their backyard telescopes. Cancer patients who said that following the mission had given them something beautiful to focus on during their treatment. Parents who had watched the final descent with their children and had tried to explain why the adults in the room were crying. These letters spoke of wonder, of inspiration, of the way that Cassini had helped people feel connected to something larger than themselves. They spoke of the mission as a source of hope during difficult times, as proof that humanity was capable of extraordinary things when it chose to work together rather than tear itself apart. They spoke of the ending not as a loss but as a gift, a demonstration of responsible stewardship, of love for the worlds we explore, of the kind of ethical foresight that the future will require of us in ever greater measure. Consider, for a moment, what Cassini's sacrifice meant in the larger sense. Here was a machine built by one species on one small world, sent across 1 billion miles of void to study another world and its moons. And when the time came for that machine to die, its creators chose to destroy it rather than risk contaminating the very places it had helped them understand. They put the integrity of alien environments above the life of their own creation. They prioritized the future over the present, the unknown over the known, the possibility of life they had never met over the continuation of a mission they had devoted their careers to. This is unprecedented in the history of exploration. When European ships crossed the Atlantic, they brought diseases that devastated indigenous populations. When settlers moved west across America, they transformed ecosystems that had existed for millennia. When humans first set foot on the moon, they left behind trash and footprints and flags that will endure for millions of years. We have not historically been careful visitors. We have taken what we wanted and left our mark wherever we went, and we have rarely paused to ask whether our presence might cause harm to things we did not yet understand. But Cassini was different. Cassini was the beginning of a new kind of exploration, one that holds itself to a higher standard. The grand finale was an act of environmental ethics extended across interplanetary space, a recognition that the cosmos does not belong to us, that we are guests in a universe far older and stranger than we can comprehend, and that our responsibility to that universe does not end when our missions do. This is the deepest lesson of Cassini's ending. It is not just that we can explore the solar system with skill and precision. It is that we can do so with humility and care. We can be the kind of species that destroys its own spacecraft rather than risk contaminating a moon that might harbour life. We can be the kind of species that chooses protection over convenience, responsibility over extension, the integrity of the unknown over the expansion of the known. Silence is not the same as gone, and death is not the same as ending. Cassini's atoms are part of Saturn now, scattered through the upper atmosphere, mixed with the hydrogen and helium and ammonia clouds that form the planet's endlessly churning weather systems. In time, those atoms will sink deeper, carried by currents we can barely imagine, into regions of pressure and temperature that no human instrument has ever measured directly. They will become part of Saturn in a way that is permanent and irreversible, as much a part of the planet as the ancient gases that were present when it first condensed from the solar nebula 4.5 billion years ago. And so the story does not end. It continues in the Saturnian atmosphere, in the data archives, in the textbooks being written and rewritten, in the minds of children who look up at the night sky and ask their parents what that yellowish star is and what we know about it. It continues in the Dragonfly mission now being built, in the Enceladus proposals being refined, in the generation of planetary scientists who chose their careers because of what Cassini showed them was possible. It continues in you, listening to these words, carrying this story forward into your own life, and perhaps someday passing it on to others. It is worth pausing on the sheer improbability of what happened here. A species evolved on a small rocky world, orbiting an ordinary star in an unremarkable corner of an average galaxy. That species developed intelligence, developed curiosity, developed the capacity to wonder about the lights in the night sky. It invented mathematics and physics and chemistry, invented telescopes and rockets and spacecraft, invented the very concept of exploration. And then it sent a piece of itself to the ringed giant 1 billion miles away, and for 13 years it used that piece to study a world that no human being had ever visited, and perhaps no human being ever will. The odds against this were astronomical. At every stage of the process, things could have gone differently. The mission could have been cancelled for lack of funding. The spacecraft could have failed during launch or during its long journey to Saturn. Any one of 1,000 engineering challenges could have proven insurmountable, but none of them did. Cassini succeeded because thousands of human beings across dozens of countries devoted their working lives to making sure it would succeed. They solved problems that had never been solved before. They built hardware that had never been built before. They navigated a spacecraft through a ring system that had never been navigated before, and when the time came, they let it go with grace. Return with me one more time to those final seconds of the mission. Cassini is deep in Saturn's atmosphere now, its thrusters fighting a losing battle against the drag of increasingly dense gases. The spacecraft's skin is beginning to heat, beginning to glow, beginning to soften and deform under stresses it was never designed to endure. The antenna that has maintained its lock on distant Earth for so many years is beginning to turn away despite the thruster's best efforts. The radio signal that has carried so much data across so much space is beginning to falter. And then, in a moment that no human being witnessed directly, the spacecraft comes apart. The delicate instruments that mapped Titan's methane lakes and tasted Enceladus's geysers and counted the particles in Saturn's rings, they separate and tumble and begin their own long falls into the planet's depths. The golden high-gain antenna that spoke to Earth for 2 decades detaches and cartwheels through the alien sky. The plutonium power source that kept everything running continues to generate its steady warmth even as it descends, a small hot point of heat being carried down toward regions where the temperature will soon exceed anything it ever encountered in space. Within seconds, everything that was Cassini has become a shower of fragments, each one trailing its own brief streak of incandescent light through Saturn's upper atmosphere. Within minutes, those fragments have cooled and dispersed, spread across hundreds or thousands of miles, invisible against the planet's banded clouds. Within hours, they have sunk deep enough that even if some future spacecraft were watching from above, it would see nothing, no trace, no evidence that anything had fallen. Within years, they will have mixed so thoroughly with Saturn's atmosphere that their atoms are indistinguishable from the native hydrogen and helium that have been there since the solar system was young. This is how the mission ended, and this is how everything ends eventually. Dispersed and scattered and mixed back into the great churning flux of the cosmos. But between the beginning and the ending, between the first gleam of possibility in a scientist's imagination and the final fade-out of a radio signal across interplanetary space, there is the middle. There is the doing. There is the mission itself, with all its discoveries and disappointments and triumphs and sacrifices. And that middle is what matters. That middle is what we get to keep. Spare a thought, too, for the people who will never see Saturn's rings except in pictures, who will never stand in mission control during a spacecraft's final moments, who will never know the particular joy of being the first human being to see a new image from 1 billion miles away. Most people will never have those experiences. Most people will live their entire lives on this one small world, never travelling farther from its surface than an airplane can carry them, never touching any ground that is not made of earth, and yet those people can still participate in what Cassini accomplished. They can look at the photographs, they can read the papers, they can follow the discoveries as they emerge from the data archives. They can feel the wonder that the mission team felt, even if they feel it second-hand, even if they feel it years or decades after the spacecraft itself fell silent. This is one of the miracles of exploration. It belongs to everyone who chooses to pay attention. You do not need to be a scientist to marvel at the hexagonal storm at Saturn's North Pole. You do not need to be an engineer to appreciate the elegance of a gravity-assist trajectory that uses the planets themselves as accelerators. You do not need a degree or a budget or a badge to stand beneath the night sky and find Saturn with your naked eye and know that there, at that steady yellowish point of light, something extraordinary happened because your species made it happen. And so, we come to the ending at last, though it is not really an ending. Cassini is gone, yes, its substance scattered through the clouds of a world it devoted itself to understanding. But the mission continues in every mind that holds its story. It continues in the questions still being asked, the data still being analysed, the children still being inspired to wonder what else might be out there waiting to be found. Saturn is still there tonight, still turning its stately 29-year orbit around the Sun, still wearing its rings like a crown of light, still holding its moons in their intricate gravitational dance. Enceladus is still venting its geysers into space, still hinting at warm oceans beneath its icy shell, still offering the tantalizing possibility that life might already exist somewhere other than Earth. Titan is still shrouded in its orange haze, still hiding its methane lakes and its dune fields and its cryovolcanoes, still waiting for the day when a rotorcraft called Dragonfly will descend through its atmosphere and land on its alien shores. All of this is still happening right now as you listen to these words, and it will still be happening long after both of us are gone. This is the gift that Cassini gave us. Not just the data and the images and the discoveries, but the reminder that the universe is vast and strange and beautiful beyond all telling, and that we are capable of reaching out to touch it if we choose. We are a species that builds spacecraft and sends them to other worlds. We are a species that asks questions and seeks answers and refuses to stop wondering. We are a species that can, when we are at our best, put aside our differences and work together toward goals that will not pay off for decades. We are a species that can love something enough to let it go. And so, as this story draws to its close, I want you to carry something with you into sleep. Not the grief of the ending, though the grief is real and it is earned. Not the loneliness of space, though space is lonely beyond all human reckoning, but the wonder, the sheer, persistent, inexhaustible wonder of it all. The wonder that we are here at all, that anything is here at all, that there is something rather than nothing, and that the something includes ringed giants, and icy moons and geysers venting into the vacuum, and a spacecraft that travelled 1 billion miles to bring us the news. Cassini is part of Saturn now, and Saturn is part of us, and we are all part of the same vast cosmic story that began with the Big Bang and will continue long after our sun has burned out and our planet has been swallowed, and our species has either spread to the stars or faded into the fossil record. We are here for such a short time, each of us, just a few decades of consciousness between two great silences. But in that brief window of awareness, we get to see things that earlier generations could not have imagined. We get to hold images of other worlds in our hands. We get to know, with scientific certainty, that the universe is stranger and more beautiful than any mythology ever proposed. Thank you for travelling out to Saturn with me tonight, for staying with this story through all its twists and turns, for caring about a spacecraft you never met, and a world you will never visit. Thank you for being the kind of person who wants to know what is out there, who finds comfort in the vast darkness rather than fear, who understands that silence is not the same as gone. Saturn is still there, still catching the light of a distant sun, still waiting for the next spacecraft we choose to send. Keep looking up, take good care of one another, and good night.